So let's have a look at using our vectors to solve problems. In dynamics, often we're more interested in breaking it up into what's happening horizontally and vertically, because it's a lot easier to work with motion in a straight line, horizontally and vertically, rather than looking at it at an angle. And so then, when you have got it in those components, once you've solved the problem, you can then resolve it back into one vector and answer the situation. So a simple example of that, you've got a plane travelling south, 100 kilometres per hour. It has a tailwind of 25 kilometres per hour. What's the plane's resultant velocity? So there's our plane, 100 kilometres per hour, and wind's blowing 25 kilometres per hour. Now they're going in the same direction, so we just simply add the two together and it would be like travelling at 125 kilometres per hour. Nice and easy when they're in the same direction, okay? But let's say they're in two different directions. So now, plane's still travelling south at 100 kilometres per hour, but now our wind is blowing sideways at 25 kilometres per hour. So when we combine those, we end up with, well, our resultant's like the hypotenuse of that triangle there. So 103 kilometres per hour. So even though that wind's not going in the same direction, it still has an effect on the velocity of the plane. Remember, force is a vector, so it has direction. So we've got these forces, three forces. One's in the direction 3i plus 2j, others 6i minus 4j, and a third one 2i minus j. So what is the resultant force? So all these forces are acting on a particular particle. What's the result of them all? Well, we simply just add them all together to find out what the result is. And so we'd end up with 11i minus 3j. Here we go. You like the pictures I found? So we've got a tractor pulling a barge along a canal and pulling it with a force of 400 newtons, and the barge moves parallel to the bank. We want to find the component of force in the direction of the motion. So direction of the motion is horizontal. Well, we could do it using projections. And we say, well, what we'd like to do is to project our vector onto the horizontal one. So I've called the T being the one at the angle there, and B being the horizontal one. So we saw that the projection is magnitude of, well, in this case T, cosine of theta, and it's in the horizontal direction, so I'll just say I for that would be the unit vector in the horizontal direction. And the magnitude is 400, we've been told that, and the angle we've been told as well, makes life nice and easy, 400 cos 14. Oh, well, there's the answer. The reality of when I'm solving a problem like that, though, I don't worry about writing down projection B and so on. I just look at the triangle and think about it. And, well, if the angle here is at 14 and I want the horizontal component, well, the horizontal component is adjacent to the angle. And I know cosine is adjacent. So I'll just go, oh, well, it's the hypotenuse times the cosine of 14. If I wanted the vertical component, then I'd say, oh, hang on, that's the opposite side. That means I've got sine, because sine is opposite over hypotenuse. And I'd just simply say, oh, well, that's 400 sine 14. In reality, I would not write down projection of T on B and all that. I just write the 400 cos 14 straight down, or the 400 sine 14 if it was the vertical one. So let's go to this problem then. We have a massive 5 kilograms on this lovely inclined plane. They love inclined planes. And it's 30 degrees it's inclined at. We have a frictional force of 15 newtons, and we're told it's acting up the plane. Just out of interest, why would it be acting up the plane rather than down the plane? Yeah, see, if we're just going to plonk it on the plane, you'd think logically it would want to slide down. Friction always opposes the motion. So friction is going up in this case. We want to find the acceleration of the particle down the incline and the reaction force. Whenever you've got an object meeting a surface, there is a reaction force at 90 degrees to the surface. Which Newton's law is that? Is that the third law, isn't it? Yep. Equal and opposite reactions, yeah. It's what basically stops you collapsing to the ground. because gravity wants to pull you down. So why aren't we all going, oh no, gravity, gravity? We're not, because there's a reaction force keeping us up as well. So, all right, I want to resolve it. In this case, though, I'm not going to resolve horizontal and vertical. And we said we don't have to. We can resolve, we just want them at right angles to each other. Now, it makes more sense if I want to work out the reaction force. Well, I'm going to resolve in the direction of the reaction force. And at 90 degrees to that would be the direction of the plane. So that's where I'm going to resolve. So I draw myself up a right angle triangle for the force due to gravity, because it's the other force there, and it's not in either of those directions. So I want to resolve it out, break it into those two components. There's my right angle triangle. I just have to work out where 30 degrees goes in this triangle. So a little bit of geometry, and we can work out to be that angle down the bottom there. So now I know where the angle is. I know that the blue one would be 5g, well that's adjacent, cosine 30. And the black one up here would be 5g, the sine of 30, it's the opposite side. So if I just look at the forces going down the plane, then going down the plane, I always make the direction that I'm travelling positive. I just think it makes life easier that way. So down the plane's positive. You'll notice my vector for the black force there is going down. So it's in the positive direction, because the same direction in which I'm travelling. And so that was 5g sine 30, but minus, because it's in the opposite direction, the frictional force there of 15. Well, we can just sub in the numbers now, and I'm assuming 9.8 for gravity here. And we get 5, because force is mass times acceleration. And we know the mass is 5. So 5 times the acceleration is 9.5. We get 1.96. So we've got the acceleration of the particle. Now we want to find the reaction force. Okay, so now I'm going to look at the forces perpendicular to the plane. So forces perpendicular will be the reaction force. I've made the reaction force positive in this case. Reason I can do that, it actually doesn't matter in this one, because it's not moving. If you think about the direction of the reaction force, it's not moving in that direction at all, because remember, it's just sliding down the plane. It's not like it's jumping off the plane, so it's staying on there. So it doesn't really matter which one I make positive. So I've made the reaction force positive. Now, if we have a look at our blue vector, it's going in the opposite direction. So that means my 5g cos 30 is negative. And remember, there is no force perpendicularly in total, because it's not jumping up, it's not falling through the thing. So those forces add up to 0. So then we get R equals 5 root 3 on 2g. See, because it equals 0, I guess that's another way of explaining why it didn't matter which way I made positive. Because if I had made the other direction positive, I would have got negative R plus 5g. It still creates the same equation. So 8F, we have a little bit of play.